Pipe. That's enough for this. I need a different type of vehicle for the database. So I'm planning on doing this one. Okay. This goes into some of my problems with terrain colliding. And it actually goes into some more interesting things like being able to mud through the terrain, changing changing it with the tires, rolling through it with heavy mass. Cool. Look at the equation.
The only way to test the durability.
Hey everyone, in this video I'll be explaining anti-roll bars. Now anti-roll bars are also called anti-sway bars or sway bars. Inside and it'll connect.
So, I'll watch that later, but probably like make a good blown 3D model of this. Simulate own version of this. See to compare. What I was going for, yeah, something like vehicle types. State multi-threaded. Yeah, I was reading about this. Oh, it's the same page. Sheet mapping. This is very similar to the Havik physics code. Or, what was it? Who made Havik? Havik did. Havik physics. I gotta go look here for a sec. It's a physics engine, it's not Havik. Valve Havik physics. But the vehicle code looks so similar. Just you didn't get access to parts of it. Parts that did some of this, I guess. Anti-roll bar, tire modeling, engine torque differentials, clutch. I wish I knew more about like fixing car mechanics, like actually doing it by hand. I guess I could replace my oil or something. My spark plugs. I have to, I don't know, probably pour in some more steering fluid and just make sure the car doesn't blow up. No, actually the car won't blow up. It's fine, but Yeah, this is where they have the snippets, the SDK. I should just go download the SDK. I remember downloading the Havik SDK. It was pretty fun. Gotta go play a game where you just like you're semi running through things, something like that. It's a pretty cool like tech demo game that Havik has. I'm not gonna go into all of this, but Microsoft. That's sad. That made me sad right there. Source one, V, physics engine. I don't want to read it. Yeah, I think it's Havik. So it's like talk about it. But basically, this is what you get. Source. The problem is can't have too many of it. You have to like it's not Battlefield, a bunch of stuff. It's just hard to compile a map. It's kind of boring actually the way it working in that example. Yeah, either it's too bouncy around, but then there's cool things like um, pulleys and the rotational stuff. The Gmod uh, items you could spawn for physics, welding. I need to look at the code itself. This right here is interesting. How much money you get for killing certain units. It's like an add-on to the game. Because of this map, the way they scripted it. Just the map, the game allows for scripting in the map editor, so it's cool. It's like almost like StarCraft 2. People making maps. This is old, 10 years old, or then the game still is played. Still do stuff. It's not limited like freaking prison like Overwatch, where it's just you get some deagles, you get some tattoos inside. What? It's the gear of the game, the tech of it. the visual tech is really cool in that game. It's just the arcadeness. It's arcade tech. That's what it is. So a player gets 2,000 for killing a refinery, and their allies get 500. Oh, I didn't know the allies get rewarded. That's cool. It's an interesting one. I'll make a new version. Uh, how to do this again? I need to memorize how to render the texture. Uh, I mean, this is different in a lot of things. Display buffer. I mean, render buffer, frame buffer, another frame buffer with different cameras. It's pretty simple to do actually in Lumberyard. Yeah, there's one thing that's kind of funky about it. Okay, I'm gonna go into the material editor and the UI editor. It'll be a little clunky, but we'll just add it on this. Call that render hammer tank. Then we have to go here. Let's use extra. I'm gonna separate these. I'm gonna tell it to render the dollar sign. I don't need the parameters. I just need this. There's like a little scroll out here. Yeah. Mm. Mm. Okay. Mm. Like an hour. An hour. So I could draw the tank behind this. So I want to set up 4 of these. How do we scale it? Not sure if I'm doing it right. Well, whatever. Just get it to look like I want it to look for now. Tank multi-render render texture. So let's see what happens when we load this asset. We need to add another one, by the way. We need to how do we name that? I want to copy paste it. Triple cannon tank. I want to have a good name. Save. Exit. Okay. Save. In here. Save. Add it to the tank. I'm now doing it backwards, but it seems to let me do it as long as I select it through this. And it also spawns some portal-looking things on the tanks and around them. Try to teleport them. I'll do that next. Okay. We need to load a reference asset. I'm gonna have 2 UI canvases running at once. Oh, whatever. See what happens. Doesn't look what I did. It might be in insert mode. Trying to figure out what even happened. It hasn't. We haven't been launched in. Yeah. There it goes. See what the debug exception was, because I kind of did nothing wrong, I feel like, but I know I did. But just, what was the reason? Switch into game, and to switch, I switched into game. Compile editor, slice, in some bus. Was there any message? Build game as expected. Added more than one runtime component. Unspectacularly. Maybe it's supposed to be doing that. I pressed F5 to continue through the breakpoint. As soon as it continues, it should display our screen here. The two first screens on the right, or it's the left and the bottom, is the small tank, and the other fourth screen is, well, it's fourth because the first is the main screen, is the big tank that I'm kind of moving slow and trying to get the box back to it was. Oh man, the stupid box ran away. The other screen could be the box. I'll make it the box. That way we could right away, before we get started with anything, have the screen asset available and then just be able to deload it. It's more of a debugging tool, so I don't know, I'm just going to build a bunch of little tools with this. Let's do it. Let's select the box somehow. It'd be nice if we could just get Ren to do a few things. I feel bad for not following through on their animation so far, because I need to do the tank next. So take a look at that next, maybe. So render texture again. I'm gonna add a few more render textures actually around the map to really abuse our call it plain character. Give it some character and its naming convention of a texture name. Material editor. Do we need the $sign in here? I believe so. Need it in a few places. Some places, yeah, they don't need it, like the material name, but it's good to have them identical for don't confuse what you're using and what. So there we go, UI canvas again. Sucks how we have to close everything down, make sure we save right. It's getting there. Well, as long as the debug isn't break. Okay, so it's time to change our other monitor. Tank. I like high tech here. Okay. Let's play. Got to change, be able to change the central camera like I was promising before. But why is it rendering off of that though? I think I did it wrong. I don't know. I mean, I did do it right. Oh, it's this key that gets me here. I see under the tank over there. Uh-oh. I lost the tank. Where'd the tank go? So you know where the tank goes now. Get more cameras. Small tank though, this is annoying. Oh my god. Is it that? I don't know. Change the camera here a little bit. Or we could maybe change where the render component camera is. Huh. I feel like if I was using the mouse with this tank, it'd be so much more fun. Changing the Y and X axis. Hmm. So I could be using the other keys simultaneously. I'm going to try to use both arms. I need to fix the UIs though. Let's try this again. Play from start. More active. I've got two objects in here that are kind of fast. Okay, I want to crash into myself. Oh, I can't tap too fast. If I super tap, I get the restart. It's going to be a teleport back button. E R Y. And we need more input. Oops, let's get to this wrong. Let's try to redo the hammer tank a little different here. We're going to have a render to texture camera. We can have a main camera also. They're a little bit different, but they're kind of the same because they both use render buffer at some point. But one gets to the render buffer at the end result. Let's select the hammer tank and kind of remove this for now. Oh, it says it's camera. Hammer tank 1 is its camera. Camera rig and position. Camera rig position entity hammer tank. I'll call this origin. And then duplicate it. Texture. And there could be like a third person and driving for both or something. And then I want the camera to be like this. The rig is right here. The origin still. This is still the origin, which is good. So I want the rig in the in between. And then multiple cameras types. And so if the camera type is being switched, that camera type wrapper can be attached to the camera rig, the origin, and behave properly later. So it's easier to organize it for different vehicles. That's, I guess, the hardest to start out with. And then everything else is pretty simple, like build a map, just add particles and spam asset. to render this texture. Let's pick a different camera. Let's try this. Didn't get it? Oh man, why is their little tank still like stupid? It looks like he's backwards. Why is the camera backwards? The other part I don't like about render texture is they made it look like source also. It's not source, it's DirectX here, causing this boxiness. But the boxiness is actually kind of cool, because it's like another shader on top of the shader. I mean, obviously this causes more frames per second drop, but that's okay. For its coolness, it's acceptable with the user, right? God, can't they just do this? I don't want to disable multi-GPU mode. I don't want to disable the Vortex. I mean the VO, the Vox Octet Global Illumination. SVOGI gem. Because it's like, uh, those can draw cool things easy. I don't care. This is what I think what I need. So when I press cancel button, oh wow, get a little cancel in here. Did that, okay. No, didn't fix the problem. Oh, this is the backward tank. Okay. but that really didn't fix my problems. Need to be switching the cameras around. So now I got 4 render to textures in order to have switching cameras around, have proper render textures in place. Let's add one thing. Then I gotta start switching the cameras actually manually. This is like stupid. Oh yeah, I was gonna do portals instead. I don't want to do that. Since it took over my camera, I'm gonna force it to work this way too, for now. See, let's try. I see myself and like have still good eye coordination with everything. That's what I'm looking for. I like easy mechanical coordination for being able to control this. It'd be more interesting if I saw the keys too separately for all the views. Hmm. The big tank, or big tank. It's also the grid rules. The one I did was for portals. I'll just load the map real quick. Uh, which one was it? I just started loading through all the levels. My terrain just dies. Oh no. Hmm, not this one. Alright, so little portal example. I don't remember. Can I move around in this or no? I think it's gonna move around in this, right? So this is also some plane with one of its materials to be a render to texture, but behind the render to texture primitives, there's nothing. Like add another primitive and just draw behind it. Display that it's there. So the idea here was just play with it in the editor, it's fine. I could demonstrate the physics works, but it's okay. I think that's a camera, the render. Yeah, and then the camera is part of this portal. So the portal itself is like a thing, and I guess um, an area nav mesh. Teleporter one. Do it. Navigation area. No, it's gonna be an area, but trigger area scripting. Let's try that. What do we? Box shape. Yes. Edit. Um. Tall. 10. Wide. 4. Thin. Whatever. Can we actually see it though? There's ways we can make it see it though. Oh, it's over there. It's got to be around this thing. Oh, it's too big. Make it 4. 2, I guess. Getting closer. The idea is on object touches box shape, it teleports to other place. That would be the basic way of getting it to work, but it's not exactly how you would see it in source, because you can still see here it's artifacted. It's not being drawn. Like in the Portal game, it's different. So you would have to rebuild a lot to get it to work the other way. Or maybe you run those commands that disable a lot of cool stuff. Why would you disable multi-GPU for this? It's like counterintuitive. I don't know. Maybe. Who cares? Bad error. Probably means add my rig attachment tactics strategies are probably failing on the high level. I have to automate some of this. Interesting. I can see that it's not drawing the grass in this. The render to texture. It'll be a good radar. Try it to add it as a radar. We want to be able to switch to the main camera though. And terrain collision map. Maybe I gotta do that in the particle editor. Gotta have this thing probably. What I didn't find here yet float or number or decimal. Decimal might be a better data type to use within SQL like database. If I have this and the values, just generate the C++ code for the components. If it doesn't include it yet, and also do it with the Python somehow. Maybe avoid some autocode generation crap that doesn't even need to be done in the first place. It's a different table. It's like stuff like this stuff's crazy. Could have added creation date and update date, but this is kind of like my base types for everything. So I could do a character string key search and have a fast ID for indexing, for using indexes very fast. Doesn't really matter though, I don't know, they're going to all this new database garbage thing. There's ways to do that too though. This is based on this algorithmic shit. I also paste in parts of this code right into my thing right now. Whatever. Keep going. It's like long pause for no reason. Different type like mechanical components of math for this. Springs, right? Main springs. And I can make these functions also in SQL for whatever reason. And roll bar. So I guess that's you don't tip over like the thing does all the time. This will be float attachment thing. And the stabilizer. I don't know what they're talking about for physics class. Just don't have time to read all of it right now. I want to read it through the text-to-speech. I think I downloaded some programs. Code project. Alright, or just screw it. It's always just screw it because not PDP. Use that or something. This site with it. That's kind of important stuff here.
Next previous NVIDIA Physics SDK 3.4.0 Documentation User's Guide. Vehicles. Introduction. Physics support for vehicles has been significantly reworked in 3x. In place of the NXWHELSHAPE class of 2.8x. A more optimal integration of the core Physics SDK and vehicle simulation code has been developed. More specifically, the vehicles component now sits outside the core SDK in a manner similar to Physics extensions. This change allows vehicles to be updated in a single pass as well as promoting a more intuitive approach to modeling vehicle data. Vehicles support has been extended from the suspension/wheel/tire modeling of 2.8x to a more complete model that couples modular vehicle components including engine, clutch, gears, autobox, differential, wheels, tires, suspensions, and chassis. A quick glance at the data structures in PXVEHICLECOMPONENTS.h will provide a flavor of the behaviors supported by Physics vehicles. Algorithm. The Physics Vehicle SDK models vehicles as collections of sprung masses, where each sprung mass represents a suspension line with associated wheel and tire data. These collections of sprung masses have a complementary representation as a rigid body actor whose mass, center of mass, and moment of inertia matches exactly the masses and coordinates of the sprung masses. This is illustrated below. Images/rigidbody.png. Figure 1a, vehicle representation as a rigid body actor with shapes for the chassis and wheels. Note that the wheel rest offsets are specified relative to the center of mass. Images/carsprungmass.png. Figure 1b, vehicle representation as a collection of sprung masses of mass M1 and M2. The relationship between the sprung mass and rigid body vehicle representations can be mathematically formalized with the rigid body center of mass equations. M equals M1 plus M2. XCM equals M1xx1 plus M2xx2 slash M1 plus M2, where M1 and M2 are the sprung masses, X1 and X2 are the sprung mass coordinates in actor space, M is the rigid body mass, and XCM is the rigid body center of mass offset. The purpose of the Physics Vehicle SDK update function is to compute suspension and tire forces using the sprung mass model, and then to apply the aggregate of these forces to the Physics SDK rigid body representation in the form of a modified velocity and angular velocity. Interaction of the rigid body actor with other scene objects and global pose update is then managed by the Physics SDK. The update of each vehicle begins with a raycast for each suspension line. The raycast starts just above the top of the tire at maximum compression and casts downwards along the direction of suspension travel to a position just below the bottom of the tire at maximum droop. This is shown in the diagram below. Images/car raycast.png. Figure 2. Suspension limits and suspension raycasts. The suspension force from each elongated or compressed spring is computed and added to the aggregate force to be applied to the rigid body. Additionally, the suspension force is used to compute the load that is bearing down on the tire. This load is used to determine the tire forces that will be generated in the contact plane and then added to the aggregate force to be applied to the rigid body. The tire force computation actually depends on a number of factors including steer angle, camber angle, friction, wheel rotation speed, and rigid body momentum. The aggregated force of all tire and suspension forces is then applied to the rigid body actor associated with the vehicle so that the transform may be modified accordingly in the next Physics SDK. Update. In addition to being collections of sprung masses, Physics vehicles also support a variety of drive models. The center of the drive model is a torsion clutch, which couples together the wheels and the engine via forces that arise from differences in rotational speeds at both sides of the clutch. At one side of the clutch is the engine, which is powered directly from the accelerator pedal. The engine is modeled as a rigid body whose motion is purely rotational and limited to a single degree of rotational freedom. At the other side of the clutch are the gearing system, the differential and the wheels. The effective rotational speed of the other side of the clutch can be computed directly from the gearing ratio and the rotational speed of the wheels that are coupled to the clutch through the differential. This model naturally allows engine torques to propagate to the wheels and wheel torques to propagate back to the engine, just as in a standard car. The data describing each component of the Physics vehicle can be found in section Tuning Guide. First code. Vehicle SDK initialization. Before using the vehicle SDK, it must first be initialized in order to set up a number of threshold values from various tolerance scales. This is as straightforward as calling the following function. Export bool pxcallconv vehicles.
What did she say?
pxbhysicsand physics. pxserializationregistry times serialization registry equals null.
Start calling
This
that.
function should be called after setting up the required pxbhysics and pxfoundation instances. If vehicle serialization is required, a pxserializationregistry instance needs to be specified.
It does.
A pxserializationregistry instance can be created with pxserialization, create T-serialization registry, C-serialization. The basis vectors of the vehicle simulation must also be configured so that longitudinal and lateral tire slips may be unambiguously computed. Void pxveclectbasisvectors, const pxvec3 and up, const pxvec3 and forward. This function can be called at any time prior to the first execution of pxvehicleupdates. The rigid body actors associated with vehicles can be updated either immediately with velocity modifications or updated with an acceleration that is applied in the next Physics SDK simulate call. The following function can be used to select the required update mode. Void pxvehicleupdatemode, pxvehicleupdatemode, enum vehicle updating mode. As expected, the vehicle SDK also has a shutdown process which needs to be invoked. Export void pxcallconvpxclosevehiclesdk. pxserializationregistry times serialization registry equals null. This needs to be called before the pxbhysics instance and pxfoundation instance are released. That is, the order of shutdown is the reverse of the initialization order. In addition, if serialization is required, the PXSerializationRegistry specified for PXNet vehicles needs to be passed to PXCLOSEVEHICLESDK.
Yeah, spawning one of these.
If vehicle serialization is used, then this must be called before closing the FISX extensions. As an illustration of the usage of these functions, Snippet Vehicle 4W has the following initialization code. PXNet vehicles *PISX PXVEHICLESCTBASISVECTORS PXVEC3 0,1 0 PXVEC3 0,0 1 PXVEHICLESCTUPDATEMODE PXVEHICLEUPDATEMODE Velocity Gange. The shutdown code in Snippet Vehicle 4W is as follows. PXCLOSEVEHICLESDK. Introduction to Vehicle Creation. The following pseudocode illustrates the basic process of setting up a PXVEHICLEDRIV4W instance. Const XU32 num wheels equals 4. PXVEHICLEWHELSSIMDATA times wheelsimdata equals PXVEHICLEWHELSSIMDATA. Allocate num wheels. Setup wheel simulation data wheelsim data. PXVEHICLEDRIVESIMDATA4W drivesim data. Setup drivesim data drivesim data. PXRIGIDDYNAMIC times Vehactor equals me physics.create origidynamic start pose. Setup vehicle actor Vehactor. Missing dotted actor asterisk Vehactor. PXVEHICLEDRIV4W times VEDRIV4W equals PXVEHICLEDRIV4W. Allocate num wheels. The drive 4W dash greater than setup physics. The 4 walker asterisk wheelsim data drivesim data num wheels 4. Wheelsim data greater than free. The code above first instantiates a PXVEHICLEWHELSSIMDATA instance with internal buffers that are large enough to store configuration data for 4 wheels. This configuration data includes fields such as suspension strength and damping rate, wheel mass, tire stiffness and suspension travel direction. The next step is to create a PXVEHICLEDRIVESIMDATA4W instance. This structure stores the configuration of the drive model and includes data fields such as engine peak torque, clutch strength, gearing ratios, and Ackermann steering correction. Following this, a PXRIGIDDYNAMICACTOR is instantiated and configured with geometry for the wheels and chassis as well as dynamic properties such as mass, moment of inertia, and center of mass. The final step is to instantiate a PXVEHICLEDRIV4W instance and associate it with the actor and the vehicle configuration data. The functions setup wheel simulation data, setup drivesim data and setup vehicle actor are actually quite involved and shall be discussed in future sections. Setup wheel simulation data, setup drivesim data and setup vehicle actor. Introduction to vehicle update. The FISX Vehicles SDK utilizes batched scene queries to query the geometry under each tire. A more detailed discussion of FISX batched scene queries can be found in section Batched Queries. The following pseudocode initializes a batched scene query with buffers large enough for a single vehicle with 4 wheels. PXRAYCASTQUERYRESULT results 4. PXRAYCASTHIT skit buffer 4. PXBATCHQUERYDESC desk 4 0 0. SQDESC.query memory.userAcast result buffer equals results. SQDESC.query memory.userAcast buffer equals skit buffer. SQDESC.query memory.raycast buffer size equals 4. SQDESC.prefilter shader equals me filter shader. pxbatchquery times batch query equals scene greater than create a batch query, skdesk. The pxbatchquery instance is typically instantiated as part of the initialization phase and then reused each frame. It is possible to instantiate a pxbatchquery instance for each vehicle, or to instantiate a single pxbatchquery instance with buffers large enough for all wheels of a batched array of vehicles. The only restriction is that all batched vehicle arrays and associated buffers configured at the start of a vehicle simulation frame must persist until the end of the vehicle simulation frame. Fisk's vehicles make use of scene query filter shaders to eliminate intersections with the vehicle issuing the raycast, and with any geometry that is not to be considered as a drivable surface. More details for how to set up Me Filter Shader above can be found in section filtering. For a batch containing just a single four-wheeled vehicle, the suspension raycasts can be performed with the following pseudocode. pxvehiclewhels times vehicles 1 equals me vehicle. pxvehiclesusbnsionraycasts batch query 1 vehicles 4 results. The function pxvehiclesusbnsionraycasts performs suspension raycasts for all vehicles in the batched array of vehicles. Each element in this results array corresponds to the raycast report for a single suspension. Pointers to contiguous blocks within results are stored by each vehicle in turn as the function iterates through the vehicle's array. These memory blocks are stored by each vehicle so that they may easily query the suspension raycast results in pxvehicleupdates. As a consequence, this results array must persist until at least the end of pxvehicleupdates and must have length at least as large as the total number of wheels in the vehicle's array. The vehicles are updated with the following function call. pxvehicleupdates time step gravity friction pairs 1 vehicles null. The function pxvehicleupdates updates the internal dynamics of each vehicle, poses the wheel shapes of the vehicle's actor, and applies either velocity or acceleration changes to the actor. Depending on the update mode chosen with pxvehicleupdatemode. More details can be found in section wheel pose and section vehicle update. The parameter friction pairs is basically a lookup table that associates unique friction values with combinations of tire type and pxmaterial. The idea here is to allow tire response to be tuned for each surface type. This shall be discussed in more depth in section tire friction on drivable surfaces. Snippets. 4 snippets are currently implemented to illustrate the operation of the Fisk's vehicles SDK. These are 1. Snippet Vehicle 4W 2. Snippet Vehicle Tank 3. Snippet Drive 3. Snippet Vehicle Scale 4. Snippet Vehicle Multithreading 5. Snippet Vehicle Wheel Contact Mod. Code snippets from each of these is used throughout the guide. Snippet Vehicle 4W. Snippet Vehicle 4W demonstrates how to instantiate and update vehicles of type pxvehicledrive4W. It creates a vehicle on a plane and then controls the vehicle so that it performs a number of choreographed maneuvers such as accelerate, reverse, brake, handbrake, and turn. Snippet Vehicle Tank. Snippet Vehicle Tank demonstrates how to instantiate and update vehicles of type pxvehicledrivetank. It creates a tank on a plane and then controls the tank so that it performs a number of choreographed maneuvers such as accelerate, reverse, soft turns, and hard turns. Snippet Vehicle Drive. Snippet Vehicle Drive demonstrates how to instantiate and update vehicles of type pxvehicledrive. It creates a vehicle on a plane and then controls the vehicle so that it performs a number of choreographed maneuvers such as accelerate, reverse, soft turns, and hard turns. Snippet Vehicle Scale. Snippet Vehicle Scale demonstrates how to configure a FISX vehicle when meters are not the chosen length scale. The snippet sets up a vehicle with meters as the adopted length scale and then modifies the vehicle parameters so that they represent the same vehicle, but with centimeters as the chosen length scale. Snippet Vehicle Multithreading. Snippet Vehicle Multithreading demonstrates how to implement multi-threaded vehicles. It creates multiple vehicles on a plane and then concurrently simulates them in parallel across multiple threads. Advanced Concepts. Vehicle Creation. This section discusses the configuration of vehicle simulation data and describes how to set up an actor that will represent the vehicle in the FISX SDK. Section Introduction to Vehicle Creation identified 3 distinct phases of vehicle configuration. Configuration of wheel simulation data, configuration of drive simulation data, and actor configuration. Each of these phases is discussed in turn. Setup wheel simulation data. The following code, taken from Snippet Vehicle 4W, instantiates a PXVEHICLEWHELSSIMDATA. Void setup wheel simulation data, const PXF32 wheel mass, const PXF32 wheel moy, const PXF32 wheel radius, const PXF32 wheel width, const XU32 num wheels. Const PXVEC3 * wheel center active offsets, const PXVEC3 and chassis offset. Const PXF32 chassis mass, PXVEHICLEWHELSSIMDATA * wheel sim data. / set up the wheels. PXVEHICLEWHELDATA wheels, PXMAXNBWHELS. / set up the wheel data structures with mass, moi, radius, width. 4. XU32 I equals 0. I less than the wheels. I plus plus. Wheels I. Mass equals wheel mass. Wheels I. Moi equals wheel moi. Wheels I. Radius equals wheel radius. Wheels I. Width equals wheel width. Enable the handbrake for the rear wheels only. Wheels, PXVEHICLEDRIV for wheel order, over left. Megs handbrake torque equals 4000.0F. Wheels, PXVEHICLEDRIV for wheel order, right. Megs handbrake torque equals 4000.0F. Enable steering for the front wheels only. Wheels, PXVEHICLEDRIV for wheel order, a front left. Max steer equals PXBI * 0.3333F. Wheels, PXVEHICLEDRIV for wheel order, a front right. Max steer equals PXBI * 0.3333F. Set up the tires. PXVEHICLETIREDATA tires, PXMAXNBWHELS. / set up the tires. 4. XU32 I equals 0. I less than the wheels. I plus plus. Tires I. Type equals tire type and normal. / set up the suspensions. PXVEHICLESUSBNSIONDATA suspensions, PXMAXNBWHELS. / compute the mass supported by each suspension spring. PXF32 sprung masses, PXMAXNBWHELS. PXVEHICLECOMPUTESBRUNGMASSES. Num wheels, wheel center active offsets. Chassis offset, chassis mass, 1, sprung masses. Set the suspension data. 4. XU32 I equals 0. I less than the wheels. I plus plus. Suspensions I. Max compression equals 0.3F. Suspensions I. Max droop equals 0.1F. Suspensions I. MSBRINGSTRENGTH equals 35,000.0 F. Suspensions I. MSBRINGDAMPERRAT equals 4,500.0 F. Suspensions I. MSBRUNGMASS equals SISP sprung masses I. Set the camber angles. Const PXF32 camber angle addressed equals 0.0. Const PXF32 camber angle max troop equals 0.01 F. Const PXF32 camber angle max compression equals -0.01 F. 4. XU32 I equals 0. I less than the wheels. I plus equals 2. Suspensions I plus 0. Camber at rest equals camber angle at rest. Suspensions I plus 1. Camber at rest equals camber angle at rest. Suspensions I plus 0. Camber at max droop equals camber angle at max droop. Suspensions I plus 1. Camber at max droop equals camber angle at max droop. Suspensions I plus 0. Camber at max compression equals camber angle at max compression.
Gotta read this.
Suspensions I plus 1. Camber at max compression equals camber angle at max compression. / Set up the wheel geometry. PXVC3 SISP travel directions, PXMAX and BWHELS.
Page 2.
PXVC3 wheel centric offsets, PXMAX and BWHELS. PXVC3 SISP for CAPM offsets, PXMAX and BWHELS. PXVC3 Tyre for CAPM offsets, PXMAX and BWHELS. / Set the geometry data. 4. XU32 I equals 0. I less than the wheels. I plus plus. / vertical suspension travel. SISP travel directions I equals PXVC3 0-1, 0. Wheel center offset is offset from rigid body center of mass. Wheel centric offsets I equals wheel center active offsets I chassis offset. Suspension force application point 0.3 meters below. Rigid body center of mass. SISP for CAPM offsets I equals PXVC3 wheel centric offsets I x -0.3 F wheel centric offsets I Z. Tire force application point 0.3 meters below. Rigid body center of mass. Tire for CAPM offsets I equals PXVC3 wheel centric offsets I x -0.3 F wheel centric offsets I Z. / Set up the filter data of the raycast that will be issued by each suspension. PXFILTERDATA CRE filter data. Set up non-drivable surface CRE filter data. Set the wheel, tire and suspension data. Set the geometry data. / Set the query filter data. 4. XU32 I equals 0. I less than the wheels. I plus plus. Wheel sim data greater than set wheel data I, wheels I. Wheel sim data greater than set tire data I, tires I. Wheel sim data greater than set suspension data I, suspensions I. Wheel sim data greater than set SISP travel direction I, SISP travel directions I. Wheel sim data greater than set wheel centric offset I, wheel centric offsets I. Wheel sim data greater than set SISP for CA point offset I, SISP for CAPM offsets I. Wheel sim data greater than set IRE for CA point offset I, TIRE for CAPM offsets I. Wheel sim data greater than set SANIQUI refilter data I, CRE filter data. Wheel sim data greater than set wheel shape mapping I. The function PXVEHICLECOMPUTESBRUNGMASSES computes the sprung mass of each suspension so that they collectively match the rigid body center of mass. This is performed in the frame of the actor. It makes sense to perform PXVEHICLECOMPUTESBRUNGMASSES in the frame of the actor, because the rigid body center of mass is always specified in the actor's frame. The vehicle suspension system, on the other hand, is specified in the center of mass frame. As a consequence, the functions set Wilson tree offset, setSysp for a point offset and setIRE for a point offset all describe offsets from the rigid body center of mass. The directness of this approach can make changes to the rigid body center of mass a bit more involved than might be expected. To solve this problem, the function PXVEHICLEUPDATCMASSLOCALPOSC has been introduced, though not used in the code above. This function recomputes and sets all suspension offsets, recomputes the sprung masses and sets them in a way that preserves the natural frequency and damping ratio of each spring. Details of many of the parameters and functions above can be found in section Tuning Guide.
I don't know if that's a good idea.
The function setup non-drivably surface, which sets up scene query filter data for each suspension raycast, shall be discussed in more detail in section Filtering. Further, the link between tire type normal and tire friction shall be made clear in section Tire friction on drivable surfaces. Finally, the use of the function setWheel shape mapping shall be clarified in section Wheel pose. Setup drivers data. The following code, taken from snippet vehicle 4W, instantiates a PXVEHICLEDRIVESIMDATA4W, PXVEHICLEDRIVESIMDATA4W drivers data //diff PXVEHICLEDIFFERENTIAL4.diff diff.type equals PXVEHICLEDIFFERENTIAL4 diff type else 4WD drivers data.set diff data diff engine PXVEHICLENGINEDATA engine engine.peak torque equals 500.0f engine.max omega equals 600.0f //approx 6000 rpm drivers data.set engine data engine gears PXVEHICLEGEARSDATA gears gears.switch time equals 0.5f drivers data.set gears data gears clutch PXVEHICLECLUTCHDATA clutch
Something is falling.
CLUTCH.MSTRENGTH equals 10.0f drivers data.set clutch data clutch Ackerman steer accuracy PXVEHICLEACKERMANNGOMETRYDATA Ackerman Ackerman.accuracy equals 1.0f Ackerman.maxley separation equals
Hmm. Oh, she shut up. video quick, blah blah blah, crazy people. Want her to read. Beckman stuff.
In this installment, we review the other side of the magic formula, the one that computes lateral or cornering forces from slip angles, or grip angles. This formula is sufficiently similar to the longitudinal version of Part 21 that we can skip many preliminaries. But it's sufficiently different as to require careful exposition, leading us to define coordinate frames that will serve us throughout the rest of the Physics of Racing series. This installment will be one to keep on hand for future reference. Diving right in, just like its longitudinal sibling, this formula requires some magical constants, 15 of them this time. Again, from Genta's possible Ferrari data sheet. A0. 1.799. Dimensionless. A1. 0. 1/mn. A2. 1688. 1/kilo. A3. 4140. N. A4. 6.026. Kn. A5. 0. 1/degree. A6. minus 0.3589. Kn. A7. 1. Dimensionless. A8. 0. Dimensionless. A9. 6.111/1000. Degree/Kn. A10. 3.224/100. Degree. A11. 0. 1/mn. Degree. A12. 0. 1/kilo degree. A13. 0. 1/kilo. A14. 0. N. Where N is Newton, Kn is kilonewton, and Mn is meganewton. As with the longitudinal magic formula, there are lots of zeros in this particular sample case, but let us not confuse particulars with generalities. The formula can account for much more general cases. The first helper is the peak, lateral friction coefficient Yp equals A1 Fz plus A2, measured in inverse kilos if Fz is in Kn. Next is D equals Ypfz, which is a factor with the form of the Newtonian model, normal force times coefficient of friction. In our sample, A1 is 0, so Yp acts exactly like a Newtonian friction coefficient. In all cases, we should expect A1Fz to be much smaller than A2 so that it will be, at most, a small correction to the Newtonian behavior. To get the final force, we correct with the following empirical factor. This has exactly the same form as the empirical correction factor in the longitudinal version, but the component pieces S, B, and E are different, here. Where is the slip angle and is the camber angle of the wheel? In practice, we must carefully account for the algebraic signs of the camber angles so that the forces make sense at all four wheels. The usual negative camber, by the shop definition, as measured on the wheel alignment machine, will generate forces in the positive y direction on the right-hand side of the car and in the negative y direction on the left-hand side of the car. This comment makes much more sense after we've covered coordinate frames, below. As before, we get B from a product, albeit one of greatly different form. Where is the absolute value of the camber angle, that is, a positive number no matter what the sign of. This gives. Almost done, include and sneak in an additive correction for Pleistocene and conicity, which we'll leave undefined in this article. To arrive at the final formula. This form is almost identical in form to the longitudinal version of the magic formula. The individual subcomponents are different in detail, however. The most important input is the slip angle. This is the difference between the actual path line of the car and the angle of the wheel. To be precise, we must define coordinate systems. We'll stay close to the conventions of the Society of Automotive Engineers, SAE, as published by the Millikins in Race Car Vehicle Dynamics. Note that this may differ from some frames we've used in the past, but we're going to stick with this set. There's a lot of intense verbiage in the following, but it's necessary to define precisely what we mean by wheel orientation in all generality. Only then can we measure slip angle as the difference between the path heading of the car and the wheel orientation. First, is the earth frame, whose axis we write as x, y, z. The z-axis is aligned with Earth's gravitation and points downward. The origin of Earth is fixed w, r, t. The Earth and the x and y-axis point in arbitrary, but fixed, directions. A convenient choice at a typical track might be the center of start/finish with x pointing along the direction of travel of the cars up the main straight. All other coordinate frames ultimately relate back to Earth, meaning that the location and orientation of every other frame must be given w, r, t, Earth, directly or indirectly. The next coordinate frame is car, whose axis we write as x, y, z. This frame is fixed w, r, t. The sprung mass of the car, that is the body, with x running from tail to nose, y to driver's right, and z downward, roof through seat. Its instantaneous orientation w, r, t. Earth is the heading. Precisely, consider the line formed by the intersection of Earth's xy plane with car's xz plane. The angle of that line w, r, t. Earth's x-axis is the instantaneous heading of the car. It becomes undefined only when the car it points directly up standing on its tail or directly down standing on its nose. To emphasize, heading is measured in the Earth frame. The next coordinate frame is path. The velocity vector of the car traces out a curve in three-dimensional space such that it is tangent to the curve at every instance. The x direction of path points along the velocity vector. The z direction of path is at right angles to the x direction and in the plane formed by the velocity vector and the z direction of Earth. The y direction of path completes the frame such that x, y, z form an orthogonal, right-handed triad. The path of the car lies instantaneously in the xy plane of path. Path ceases to exist when the car stops moving. Path heading is the angle of the projection of the velocity vector on Earth's xy w, r, t. The x-axis of Earth. Millikan calls this course angle, Greek upsilon. Path heading, just like heading, is measured in the Earth frame. The side slip angle of the entire vehicle is the path heading minus the car heading. This is positive when the right side of the car slips in the direction of travel. The next set of coordinate frames is ROAD, where I varies from 1 to 4. There are 4 frames representing the road under each wheel, numbered as 1 equals left front, 2 equals right front, 3 equals left rear, 4 equals right rear. Each ROAD is located at the force center of its corresponding contact patch at the point RI equals, Rix, Re, Riz, W, R, T, Earth. This point moves with the vehicle, so, more pedantically, the origin of ROAD is RI, T, written as a function of time. To get the x and y axes of ROAD, we begin with a temporary, flat, coordinate system called tie aligned with Earth and centered at RI, then elevate by an angle -90 degrees. Consider any point P in space with coordinates P equals, px, pi, pz, w, r, t, Earth. A little reflection reveals that its location w, r, t, is pi p, ri, just subtracting coordinates component by component. To get coordinates in TBI, we multiply by the orthogonal matrix. Once again, see www.britannica.com for brush up. That does not change the y components, but increases the z and decreases the x components of points in the first quadrant for small, positive angles, namely. We pick this matrix by inspection of the figure above or by application of the right-hand rule. Yup, see Britannica. Finally, to bank the system, we need the orthogonal matrix that does not change the x components, but increases the y and decreases the z components of first quadrant points for small, positive angles, namely. In case you missed it, we snuck in a reliable, seat-of-the-pants method for getting the signs of orthogonal matrices right. In any event, given P and Ri, we compute the coordinates, Pri, of the point P in ROAD as follows. If the angles are small, and the matrix can be simplified to even at 20 degrees, the errors are only about 6% in the cosine and 2% in the sin, resulting in a maximum error of 12% in the lower right of the matrix. This matrix approximation is suitable for the majority of applications. One feature of orthogonal matrices is that their inverse is their transpose, that is, the matrix derived by flipping everything about the main diagonal running from upper left to lower right. In the small angle approximation, we get the right-hand side is very close to the unit matrix because the squares of small angles are smaller, yet with the inverse matrix we can convert from coordinates in ROAD to coordinates in Earth. The last set of coordinate frames is WHE. As with ROAD, there is one instance per wheel. WHE is centered at the wheel hub. Under normal rolling, the coordinates of its origin in ROAD are WRI equals 0, 0, RI, where RI is the loaded radius of the tire wheel combination. Pedantically, RI should be corrected for elevation and banking, but such corrections would be small for ordinary angles on the order of plus. It seems not to be standard practice. I can find no reference to it in my sources. More important is the orientation of WHE. Consider the plane occupied by the wheel itself. This plane intersects ROAD in a line that defines the x direction of WHE, with the positive direction being as close to that of travel as possible. The y direction points to driver's right. The wheel plane is tilted by a camber angle, about the x-axis of the wheel coordinate system. To emphasize, WHE does not include wheel camber, and it differs from road only by a rotation about road's z-axis that accounts for the pointing direction of the wheel. At this point, you should create a mental picture of these coordinate frames under typical racing conditions. Picture a car frame yacht at some heading W, R, T, Earth, and perhaps pitched and rolled a bit, a path frame aligned at some slightly different path heading, and individual road and wheel frames under each tire contact patch, where the road frames are perhaps tilted a bit W, R, T, Earth, and the wheel frames are aligned with the wheel planes but coplanar with the road frames. For a car traveling on a flat road at a stable, flat attitude, the XY planes of car, path, and Earth would all coincide and would differ from one another only in the yaw angles. And when some tilting is engaged, and are still defined by the precise projection mechanisms explained above. Now, imagine the x-axis of car projected on the xy plane of each wheel frame and translated without changing its direction to the origin of wheel. The angle of wheel's x-axis, which is the same as the plane containing the wheel, W, R, T. The projection of car's x-axis, defines the steering angle, of that wheel. Finally, imagine path's x-axis projected onto the xy plane of wheel in exactly the same way. Its angle W, R, T to the x-axis of wheel, in all generality, defines the slip angle. Since wheel is lilted W, R, T, gravitational down, the load, Fx, on the contact patch, which we need for the magic formula, must be computed in wheel. It will be smaller than the total weight, Wi, by factors of end, which are obviously unity under the small angle approximation. At last, we can plot the magic formula. The horizontal axis measures slip angle, in degrees. The vertical axis measures lateral, cornering force, in newtons. The deep axis measures vertical load on the contact patch, in kilonewtons. We can see that these tires have a peak at about 4 degrees of slip and that cornering force goes down as slip goes up on either side of the peak. On the high side of the peak, we have dynamic understeer, where turning the wheel more makes the situation worse. This is a form of instability in the control system of car and driver. As a final comment, let me say that I am somewhat dismayed that the magic formula does not account for any variation of the lateral force with speed. Intuitively, the forces generated at high speeds must be greater than the forces at low speed with the same slip angles. However, the literature sometimes explicitly, and sometimes by sin of omission states that the magic formula doesn't deal with it. One of the reasons is that, experimentally, effects of speed are extremely difficult to separate from effects of temperature. A fast-moving tire becomes a hot tire very quickly on a test rig. Another reason is that theoretical data is usually closely guarded and is not likely to make it into a consensus approximation like the magic formula. This is a fact of life that we hope will not affect our analyses too adversely from this point on. The Physics of Racing. Part 21, The Magic Formula, Longitudinal Version. Brian Beckman, Ph.D. Copyright February 2001. Driving a car is a classic problem in control. Here, we mean control in the technical sense of control theory, an established branch of engineering science. Once again, I find http://www. Britannica.com to have a very nice, brush-up article on that term. In a more or less continuous fashion, the driver compares desired direction, speed, and acceleration with actual direction, speed, and acceleration. The driver uses visual input to sense actual direction and speed, and uses visceral, inertial feedback the butt sensor for actual acceleration. When the actual differs too much from the desired, the driver applies throttle, brake, steering, and gear selection to change the actual. These inputs cause the tires to react with the ground, which pushes back against the tires, and through the suspension, pushes the body of the car and driver. Drivers in high-speed circumstances can also generate desired aerodynamic forces, as in slipstreaming, in the slingshot pass, and in the Earnhardt tip maneuver, where the driver takes the air off the spoiler of the car in front of him. Tires generate forces by sticking and sliding and everything in between. They transmit these forces to the wheels by elastic deformation. The elastic deformation is extremely complex and theoretical computation requires numerical solution of finite element equations. However, despite fierce trade secrecy, industry and academia have reached apparent consensus in recent years on a formula that summarizes experimental and theoretical data. This so-called magic formula is not a solution to equations of motion. A solution in such a form is not feasible. It's just a convenient fitting of commonplace mathematical functions to data. It allows one to compute forces at a higher precision than something like RARS, see parts 16 and 19 of the Physics of Racing PHOR, but without integrating equations. Therefore, forces can be computed within a reasonable time, say in a real-time simulation program. To understand the magic formula, we need first to define its inputs, which include slip. Slip is an indirect measure of the fraction of the contact patch that is sticking. It is frequently asserted in the literature that a tire with no slip at all cannot create forces. It has taken me a very long time to accept this assertion. Why can't I steer a tin toy car with metal tires on a hard surface like Formica? If there is any slip in such tires, it is microscopic, yet there are sufficient forces to brake and steer, even if just a
Remember,
little.
this, set the camera
I
to
finally caved in when I realized that the forces are minute, also. If there is any friction between the tire and the surface, there must be slip, as it is defined below.
Go get some air and
Though to a very
I'll
small
figure this
degree,
out.
the formica and the tiny contact
Or maybe I'll
patches
keep it
of
a
the tin
secret, I don't
tires
know.
actually twist and stretch each other. The only way to eliminate slip completely is to eliminate grip completely. Any grip, and you will have slip. There are two, slightly different flavors of the magic formula. The longitudinal one is the subject of this entire installment of PHOR, and we cover the lateral one in the
Trying
next
to get
installment.
the camera to
Longitudinal
switch.
slip is along the mean plane of the wheel and might also be called circumferential or tangential.
And I also
It
have
creates
this
braking and accelerating forces.
number variable I
Lateral
wanna use
slip is
as
our old
some
friend
sort
grip
of
angle
switch if logic
PHOR10,
tells
and
it
it generates cornering
later.
forces. We write longitudinal slip as
It'd be nice to
it's
write
defined by the actual
these
angular velocity
theories.
of a wheel plus tire under braking or
Script canvas, 'cause
acceleration,
it gets, like,
compared to the
gnarly.
corresponding angular velocity of the same wheel plus tire when rolling freely. We write the free-rolling angular velocity as, where v is the current, instantaneous velocity of the hub center line of the wheel with respect to the ground, and r is the effective radius, a constant defined below. Since the dimensions of v are length/time, and the dimensions of any radius are length, the ratio has dimensions of inverse time. In fact, it should be viewed as measuring radians per unit time, radians being the natural, dimensionless measure of angular rotation. There are radians in one rotation or one circumference of a circle, just as the length of the circumference is times the radius. Let's begin the discussion of longitudinal slip with a question. Consider a wheel-tire combination with 13-inch radius or 26-inch diameter, say a 255-50/16 tire on a 16-inch rim. The 50 in the tire specification is the ratio of the sidewall height to the tread width, which is also written into the specification as 255 mm understood. We get a sidewall height of 50% of 255 mm, which is 5.02 inch. Therefore, the total, unloaded radius, half of the tread-to-tread diameter, is about 5 plus 16/2 equals 13 inch. Now consider a rigid tire of the same radius, made, say, of steel or of wood with an iron tread like old Western wagon wheels. The question is whether, given a certain constant hub velocity, pneumatic tires spin faster than, slower than, or at the same speed as equivalent rigid tires. At first glance, one might say, well, faster, obviously. Since the pneumatic tire compresses radially under the weight of the car, its radius is actually smaller than the unloaded radius at the point of contact, where it sticks and acquires linear velocity equal in magnitude and opposite in direction to the hub velocity. Since smaller wheels spin faster than larger ones at the same speed, the pneumatic tire spins faster than the equivalent rigid tire of the same unloaded radius. Let the unloaded, natural radius of the pneumatic tire be r, also the radius of the equivalent solid tire. If the hub has velocity v, the solid tire spins with angular velocity. Since the loaded radius of the pneumatic tire, RL, is smaller than r, v/RL, the angular velocity of the loaded pneumatic tire must be larger than v/r. This is partly correct. The pneumatic tire wheel combination does spin faster than a rigid wheel of the same unloaded radius, but it does not spin as fast as a rigid wheel of the same loaded radius, which is the height of the hub center off the ground under load. The reason is that the tire also compresses circumferentially or tangentially, setting up complex longitudinal twisting in the sidewall. The tangential speed of a particle of tread varies as the particle goes around the circumference of the tire. Let's mentally follow a piece of tread around as the wheel, not necessarily the tire, turns at a constant radial velocity. Imagine a plug of yellow rubber embedded in the tread, so that you could visually track it or photograph it with a movie camera or strobe system as it moves around the circumference. The rubber of the tread does not travel at constant speed, even though the wheel supporting the tire does. At the top of the tire, the radius is almost exactly r, the unloaded radius, so the tread moves with tangential velocity. As the yellow plug rolls around and approaches the contact patch from the front, it slows down in the bunched up area at the leading edge of the contact patch just forward of it. There is a bunched up area, because the tire is made up of elastic material that gets squeezed and stretched out of the contact patch and piles up ahead of the contact patch as it rolls into it from the direction of the leading edge. Eventually, the plug enters the patch, in the center of which it must move at speed relative to the hub center, that is, backwards at a speed dictated by the loaded radius and the wheel velocity. We've assumed that the plug is not slipping on the ground at the point where it has speed with respect to the hub. This means that it has speed 0 with respect to the ground at that point.
I think my
The
physics
average of the
matched with
tangential
other thing.
velocities around the wheel defines the effective radius, ρ, as follows. Let measure the angular position, from 0 to, around the wheel. Suppose we knew the tangential velocity with respect to the hub center, v, at every. We could easily measure this with our strobe light and cameras. V gives us the radius at every angular position via the equation v = r, where is the constant angular velocity of the wheel. The average would be computed by the following integral. Let's run some numbers. 10 miles per hour is 14 feet/second or 176 inches/second. With an unloaded circumference of inch/revolution, we get 176/=2.154 revs per second, or 129 rpm for each 10 miles per hour. Under ordinary circumstances, the effective radius will be no more than a few percent less than the unloaded radius, and the RPMs should be, then, a few percent more than 129 rpm per 10 miles per hour. At 100 miles per hour, the tire is under considerable stress and spins at something over 1,300 rpm. Now we're in a position to define longitudinal slip, written. We want a quantity that vanishes when the wheel rolls at constant speed, increases when the wheel accelerates the car by pulling the contact patch backwards, and decreases below 0 when then wheel brakes the car by pushing the contact patch forward. Under acceleration, the wheel and tire combination will tend to spin a little faster than it would do while free rolling. We already know that, for a given v, the free-rolling angular velocity is, by definition. The actual angular velocity, then, is higher under acceleration. So, if we know v, and the constant ρ, then we can define the longitudinal slip as the ratio, -1, so that it's 0 under free-rolling conditions. Just looking at this formula, a free-rolling wheel has, equals 0, a locked-up wheel under braking has equals 0, equals -1, and an accelerating wheel has a positive of any value. The magic formula yields the longitudinal force, in newtons, given some constants and dynamic inputs. The formula takes 11 empirical numbers that characterize a particular tire B0, B1, B10. The dynamic parameters are Fz, or weight, in kilonewtons on the tire, and the instantaneous slip. The 11 numbers are measured for each tire. We borrow an example from Motor
try
plug
that
Vehicle
in
Dynamics by
later.
Giancarlo Genta.
Pretty cool. It'd be good
On
for,
page
like,
528, he offers the
semi-trailer
following
vehicles,
numbers for a car that
trailers,
appears to
and
be a Ferrari
trailer
308 or
vehicles,
328,
semis,
to which I have
cars,
added
or the
dimensions.
vehicle of war.
B0,
To have, like, a kart training,
1.65, dimensionless,
or the track
B1,
tank.
0, 1/meganewton,
There was
B2,
some really cool things about it.
1688,
You don't have to deal
1/kilo,
with the trailer with the,
B3,
like a regular pickup truck, a
0,
small one. It's funny.
1/meganewton,
But it's not
B4,
fun. But the physics are fun.
229,
Not
1/kilo,
the physical.
B5,
the
0,
benefit associated with
1/kilonewton,
and breakdowns.
B6, 0,
Breakdowns.
1/kilonewton,
Flat
2,
tires.
B7,
Yeah, but that would be
0,
cool is driving a flat tire car
1/kilonewton, B8,
like in rigor rock.
-10, dimensionless, B9, 0, 1/kilonewton, B10, 0, dimensionless. Though the majority of these values are 0 for the tires on this car,
it is by no means always the case. In fact, the large saloon example just before the alleged Ferrari in Genta's book has no zeros. We build up the magic formula in stages. The first helper quantity is P equals B1 Fz plus B2. This is an estimate of the peak, longitudinal coefficient of friction, fitted as a linear function of weight, see part 7 of 4s. From this definition, we begin to see what's going with the dimensions. A typical,
Now we got the
streetable
black
sports
hole
car might
abyss,
weigh in
no
at
textures
3,000
in this.
pounds, which is about 3,000/2.2 equals 1,500 asterisk 0.9 equals 1,350 kilograms, which is about 1,350 asterisk 9.8 equals 13,200 newtons, or 13.2 kilonewtons. Look, Ma, no calculator.
It's kind of very
Let's assume each tire
uncostly to
gets a
be
quarter
drawing
of
it.
that to
That's the
start
nice thing
off
about
with,
it.
or 3.3
Kind of
knots.
like the debug wireframe.
B1 multiplies
Oh,
that
look at the
number to
collision
give us
model I
something
made
with
for the
dimensions of
tank.
kilonewton/meganewton,
Shows it over there.
which we write simply as 1/kilo,
Let's get rid of this
inventing
very
units
bad
on the
particle
fly.
effect on
1
us.
mega equals 1 kilo squared.
What would this do?
B2
Oh,
has the same
actually works.
dimensions, so it's kosher to add it in, yielding P equals
Alright, so it's interesting in
1,688/kilo in this case.
the renders
The
inside
next
that
step is
particle
the helper
vector.
D equals Pfz, which will be in newtons. We now see the reason for the 1/kilo unit. In our case, we get about D equals 1,712, asterisk 3.3 equals 5,610, 40 equals 5,570 N. The important
Big
point is
truck.
that D is linear in
Tank
Fz,
doesn't have a
so
camera.
acts, mathematically, like a coefficient of friction, as promised. B2
gotta
is a
move
pretty
this over.
direct measurement of stickiness, times 1000 for convenience. This model tire has a coefficient of friction of almost 1.7. Not my data, man. The next step is to compute the product of a new helper, B, times B0 and the aforecomputed D. The magicians who created the formula tell us that B0D equals B3FZ2 plus B4FZ, EXP, B5FZ. This slurps up a few more of the magical 11 empirical numbers, and a pattern emerges. These bi numbers serve as coefficients in polynomial expressions over Fz. So, B5Fz is dimensionless, as must be the argument of the exponential function. B3Fz2 plus B4Fz has dimensions of newtons, as does the entire product. Therefore, B must be dimensionless. We need B in the next step, so let's solve for it now. Where we've been able symbolically to divide out one factor of Fz, convenient especially for numerical computation, where overflow is an ever-present hazard. Continuing with our numerical sample, B3Fz plus B4 equals 229/kilo, the exponential is unity, and the numerator is yielding B equals 229/2786 equals 0.0822. Most importantly, B depends only weakly on Fz. In the sample case, not at all, because B1 equals B3 equals B5 equals 0, but there are lots of other ways to characterize the algebraic dependence of Bon Fz. The next step is to account for the longitudinal slip with another helper, S equals 100 plus B9 Fz plus B10. In our sample case, this reduces to just S equals 100. Only one more helper is needed, and that's E equals B6 Fz2 plus B7 Fz plus B8, very straightforward. The final formula is, once again, don't try to find any physics in here, it's just a convenient formula that fits the data reasonably well. Plugging in numbers 4 equals 0, because that's an easy sanity check to do in our heads, we see immediately the result is 0. Let's try S equals 10, 10% slip. SB equals 0.822, tan 1, 0.822, equals 0.688, E equals minus 10, so the argument of the outer arc tangent is SB, 10 asterisk, minus 0.266, equals SB plus 2.66 equals 3.48, tan 1, 3.48, equals 1.29, 1.29 B0 equals 2.13, sin
Okay,
2.13 equals 0.848, and, finally, d asterisk 0.848 equals 4,720 newtons. Lots of longitudinal force for a 3,300 N vertical load. Let's plot the whole formula. The horizontal axis measures S equals 100, which is really just slip in percent. The deep axis, going into the page, measures Fz from 5 knots, nearest us, to 0 in the back. The vertical axis measures the result of applying the formula to our model tire, so its longitudinal force of launching or braking. Notice that for a load of 5 knots, the model tire can generate almost 8 knots of force. Very sticky tire, as we've already noticed. Also notice that the generated force peaks at around equals 0.08, or 8%. The peak would be something one could definitely feel in the driver's seat. Overcooking the throttle or brakes would produce a palpable reduction in G-forces as the tires start letting go. Worse than that, increasing braking or throttle beyond the peak leads to reduced grip. This is an instability area, where increasing slip leads to decreasing grip. Finally, note that the function behaves roughly linearly with Fc, showing that it acts like a Newtonian coefficient of friction, albeit a different one for each value of slip.
It would really go on to this thing. Or it could be the gas. Smoke, the gas, the fire. Let's see. The death ball fire. Good. Oh, cool. It renders. It's like just a fucking magma spout thing, isn't it? Particle effects are fun. That's why I don't like doing them. You just get into fucking trash making things. Trash making is cool. Just have to make the terrain work and the bending. Maybe get the MCU stuff installed. Switching the camera is really what's annoying me. Because I can't do that. I'm trying to. Oh, it's got it though. I'll be on later. I need more follow stuff.